everyone. My name is Ronit Patel and I am here to present my DA323 course project on exploring VATT transformers for multimodal learning with audio, video and text. It is a groundbreaking framework which was proposed in the year 2021 at NeurIPS. So coming to the overview, so here's our roadmap which I will be covering. First, I will cover motivation, followed by historical perspective, then key learnings, technical approach, experiment results, surprises, and at the end, scope for improvement. This will give us the full picture of VAT's role in multimodal learning. So coming to motivation, so what was the reason due to which I chose VATT for this project? So it skips supervised pre-training cost and biases, processes raw unlabeled video, audio and text data, and matches as well as beats CNNs in vision audio tasks. So it was a very surprised moment for me as well that it beats CNN in vision as well as audio task. Also, it is a scalable, unbiased approach to AI. Coming to the historical perspective, so let's look at some of the major breakthrough in that occurred in AI's evolution. So before 2017, CNN was majorly used for vision and audio tasks. LSTMs were used for handling text data. Further, in the year 2017, a paper called Attention is All You Need came, which introduced us to transformers. It transformed natural language processing with the help of self-attention. Further, BERT and GPT set records for audio, for vision, for text task for natural language processing. And by the year 2020, vision transformers or VIT came, which rivaled CNNs in image task. So coming to the rise of multimodal learning, it was started in the year around 1980s with audio-visual task. Transformers unified this field with model like video, BERT, and clip. VAT in the year 2021 pushes this further with convolution-free self-supervised learning on raw data, hitting 82.1% accuracy on Kinetics 400. Now let's come to key learning that I learned from this paper. It explores modality agnostic transformer where one backbone handles all modalities matching specific model performance. Transformer also excel this this transformer also excel with raw video, audio and text, outperforming CNN with 82.1% on Kinetics 400 and 39.4% on 39.4% MAP on audio set. Secondly, self-supervised learning via contrastive losses aligns modalities using unlabeled data like how to 100M, avoiding labeled data biases. Further, this paper uses something called drop token. It is a novel technique which manages the quadratic computational complexity of transformers, and it reduces it almost by 50%, which is a great success of this paper. Moreover, despite being pre-trained on multimodal video data, fine-tuning VAT's vision transformer on ImageNet yields a top 1 accuracy of 28.7%, which is close to vision transformer's accuracy of 79.9% and also surpasses the 64.7% achieved by training the same transformer from scratch. So coming to the approach, this paper provides us with two major approaches. First one is where the backbone transformers are separate and have specific weights for each modality, and the other one is the one where transformers share weights, namely there is a single backbone transformers applied to any of the modalities. Here we are using three types of modalities, which are images, which are videos, audio and text. So coming to tokenization and positional encoding. So VATT processes raw signal from video, audio and text into vector sequences for transformers using modality specific tokenization and positional encoding. It turns raw video into patches, audio into waveform segment, and text into one-hot vectors. Positional encoding preserve order 3D for video, temporal for audio, and sequential for text, which is required for transformer processing. These are in the slides you can see the various dimensions which is required for these for this transformer for tokenization. Now coming to the drop token part, after tokenizing video and audio inputs into sequences, drop token randomly sample a portion of these tokens, feeding only the sampled subset rather than the full set to the transformer. This is how the complexity is reduced from O(n) square, where n is the number of input tokens. Now coming to the architecture of that VATT transformer. So it mirrors standard designs like BERT with multi-head attention and MLP layers. It is kept simple for compatibility with existing frameworks, ensuring it can process multimodal inputs effectively through self-attention mechanism. So if you want to see the architecture in the detail, it is present in this image as well. I will further explaining some of the segments of this part. Earlier I have explained how these are tokenized. Further I will explain what are the losses that are being used. So coming to the common space projection. So VATT maps outputs to common spaces, which is SVA, for video audio, and SVT for video text using hierarchical projection as shown. It uses linear projection for most mappings with a two-layer setup for video, enabling cosine similarity comparison across modalities. So for GA to VA, GT to VT, and GV to VT, a linear projection is used. For GV to VA, a two-layer projection with ReLU activation between layers is applied to capture more complex transformation. So coming to the multimodal contrasting learning, these are the two losses which are used. The first one is noise contrastive estimation for video audio pairs, and other one is projection multiple instance learning NCE for video text pairs and head design. So overall the loss objective becomes NCA plus lambda times mil NCA. So coming to the experiment part. So first of all, I'll tell you about what is the pre-training setup. So for experiments, VATT pre-trains on audio set for video audio and how to 100M for triplets following YouTube policies. It uses a 50% drop token rate, common space dimension of 512 and 256, and trains with Adam over 500k steps at a batch size of 2048. Coming to the downstream evaluation part. So VAT is tested on 4 tasks across 10 dataset: video action recognition on kinetics and UCF 101, audio classification on audio set, zero shot retrieval on UCook 2, and image classification on ImageNet, proving its wide applicability. So coming to the results part, so first I would tell you about fine tuning for video action recognition. Results are impressive. VATT large score 82, VATT large scores 82.1%, which is top 1 accuracy on kinetic 400 and 83.6% on kinetics 600, topping models like Time-S Former as shown in this table. It is the first self-supervised transformer to set such benchmark in video task. Coming to fine-tuning for audio event classification. So in audio, VATT base achieves a record 39.4% of MAP on audio set, outdoing CNN-based model as seen here. It processes raw waveforms directly, and the modality agnostic version nearly matches this performance, which is remarkable. Coming to fine tuning for image classification and zero shot retrieval. So our model VAT hit 78.7% top 1 accuracy on ImageNet, showing transferability from video to images, and performs competitively in zero shot retrieval on UCook 2 and MSR VTT as per according to the table shown. This versatility despite noisy text data is freaking good. Coming to the feature visualization. So feature visualization using a TSNE, so VAT's fine-tuned representation separate better than models trained from scratch. Interestingly, modality agnostic and specific features look similar, suggesting a unified perception across data types. Now coming to the effect of drop token. Drop token effect is clear in these tables. A 50% drop rate balances accuracy and cost, cutting G flops to 375.4, while high resolution inputs with drop token match or beat low resolution ones on Kinetics 400 with accuracy up to 81.1%. So coming to the part what surprised me. So VAT's transferability, which is 78.7% on ImageNet from video data, is remarkable, matching CNNs with 82.1% on Kinetic 400. Modality agnostic success with a shared backbone is a huge success, and mastering raw data without features. And it also redefines multiple possibilities. Also, its performance is as good as in comparisons to various CNN models, which is a very good which has a very good future since CNNs are being the best models since its inception, and now we can move forward from CNNs and look forward to other models as well, such as VAT for uh, vision tasks. So coming to the scope of improvement, VAT can improve in text data quality for better retrieval, computational efficiency beyond drop token, adding modalities like depth and exploring mixture of experts for capacity. These are exciting areas for future research to enhance its impact. So thank you for your attention. I would like to acknowledge our college for this opportunity.